Hi CTM students, welcome to the lesson for 6.2. You can find it on pages 292 to 304. There's some vocabulary here that I'm going to assume that most of you are familiar with. I'm going to assume with this whole lesson that you have some algebraic or algebra experience, and I'm going to try to, for the most part, just hit what I think are common errors that students make when solving equations in algebra. And if you want to see some of the more I guess you could say easier problems or some of the more basic problems, check out your book or check out an algebra book and check out some of the beginning lessons in an algebra book, and you'll see some of the more basic type of problems here. There's actually 14, no, I think there's actually 15. Let me double check that. Yeah, there's 15 examples in the book to go along with this lesson. We're going to not do even close to that many here. I'm just going to hit the examples that I think are the most challenging or that present a certain idea that I see students make mistakes on a lot. Okay, so hopefully this will help you review your algebra skills if you are somebody that's done algebra before, or if you're relatively new to algebra, you'll see some common mistakes and you won't make those same mistakes because you know what not to do. Okay, so starting off with these, you don't have to write these properties down, but I just want to make sure you understand them and hopefully have an idea and can remember about what they are or what they say. So when I think of commutative property, I think of commuting back and forth to work. So I could say like A is my house and B is being a teacher, B is school for me. And so I'm going to drive from A to B, from my house to my work. And then when I go back home, I'm going to drive from B to A. But that distance that I've traveled is going to be the same distance. So commute, when I commute back and forth to work, I think of it like that. I'm commuting from A to B and then back from B to A, but it's the same distance. If I add those two distances together, I would get the same thing. Commutative property of multiplication works the same way, just with multiplication. So you just kind of switch the order of the numbers that you're multiplying together. The associative property, I think of associating with different people. Maybe you're close friends with, let's do this. I had this in mind before. Like Ashley and Brad, maybe they were dating and they were really close to one another. And Carl was Brad's friend, but he seemed to be the third wheel for a while because Ashley and Brad were so close. But you put them all together, they're all friends. They all add up to the same thing together. But then when Ashley and Brad broke up, Ashley was kind of the third wheel, and Brad started hanging out with Carl more again. And yeah, Ashley was kind of left out, so Brad and Carl, but you put them all back together again, yes, they're the same people. If you add, I'm sorry for that if you found that kind of silly, but hopefully that helps you remember associative property. These are people kind of associating, or variables associating differently with one another, but you add them all together, in the end you're going to get the same thing no matter if you add A plus B first or if you add B plus C first. And the same thing works with associative property for multiplication. And then finally the distributive property, we distribute through. If we have something plus or minus in between with parentheses, something times all that on the outside, we distribute the A through. We're going to do A times B plus A times C. So at this point, let's check out some examples. There are some examples of the associative, commutative, and distributive properties there too if you want to check those out. But let's check out some examples now of what I tend to see as common mistakes, or at least equations that give students some fits sometimes, some algebraic fits you could say. So let's solve for x in this equation below. So equations are things that equate to expressions, remember? So here's an expression, and I'm going to say this expression equals this expression over here, 11 minus 5 times the quantity 2x minus 3. So you might look at that and say, okay, I feel pretty good about that. I don't know what the common mistake is you're talking about, Mr. Wagner. Here, I will show it to you. It's actually done for the most part in the first step. This is the most common mistake I would see with a problem like this. So we distribute the 4. I want you to use a different color as I'm doing so here and show these steps here. So we're going to distribute the 4, but we distribute the 5. A lot of students will just like circle the 5 or think of it just as 5, but you also have to distribute the sign that's in front of that number, which is in front of the parentheses. So think of it like this. Think of distributing the negative 5. Okay, that's the common error, forgetting the sign. When we do that, let's see what we get. 4 times x is 4x. 4 times 3 is 12. and then we'll have 11, and then minus 5 times positive 2x, that would be a negative 10x. Negative 5 times negative 3 would be a positive 15. And now we put all that together and we combine like terms if possible. So right now this x and the regular numbers on the left side, right now I've got this regular number here. I can combine these like terms together. So if I've got regular numbers, or constants, we call those constants, if I have constant terms, those can go together. So I've got 11 and a plus 15 together. That's going to make positive 26. I'm going to write my x's first though. So I would have negative 10x plus 26. And then at this point, let's get that different color out again. At this point, I think the easiest way to do problems like this is to keep the variables positive as often as possible. Here, to keep it positive, rather than subtract 4x, I'm going to add 10x to both sides. So remember, it's like a balance. We talked about that in the last lesson. When I keep it balanced, you have to do the same thing to both sides of the equation, just like we added the same sort of weight to both sides of a scale in something like a science class. So this would go away here and here. That would cancel out. And you could add this together. I'm going to show this in one step. You could do this in 2 steps and just separate it. But I think most of us are probably to a point in our mathematics careers, at least if you're one of my CTM students, where you could do this in the same step, in the same line. So the x's are all over on the left side now. Now I want to get the constants over on the other side. So I would subtract 12 to do that. So that's going to go away here and here. And you're left with 14x. And it so happened to work out that it ended up being really nice here in the end. It's going to be a simple division of 14 divided by 14 to solve this problem or to finish the problem. Cancel those out there and there. You've got x equals 14 goes into 14 one whole time. And I do want to make a note, at least with this first one, that you should do this. So in the different color, you should always, with equations when possible, at least mentally check all your answers when you're done. So at least mentally check all answers when done. Yes, that's an exclamation point. I'm adamant about that. You must do it. It's going to help you. You're not going to get things wrong if you do that. Or at least you'll know if you made a mistake at the very least. So plug this back in. We've got 4 times. We'd do 1 plus 3 first. That would be 4. 1 plus 3, and then 4 times 4 would be 16. On this side, I'd have 2 times 1, which would be 2. And 2 minus 3 would be negative 1. So I'd have a negative 5 times a negative 1, which would be positive 5. Positive 5 plus 11 is in fact 16 as well. So I have 16 equals 16. If you can't do that mentally, it's always fine to write it out, write the check out, and see that it works. So I say you might as well take an extra minute or two, especially if you have the time to do so on a test, to check your answers, know if you got it right. On tests, really, that's a small portion time-wise of the class, but it's the largest portion grade-wise of the class. So I don't think it makes any sense to rush through a test to try to be the first one to hand it in or something like that. It makes a lot more sense to take your time, check your answers when possible. Let's check out a second equation now, though, to solve for x. So again, some common mistakes that I'll see, or some problems. This one's more a problem that students would look at and say, I don't know how to start this. Even if they've taken algebra and passed algebra, they seem to forget how to do something like this. And so we've got fractions. Whenever possible, it's a lot nicer not to deal with fractions in equations. And so it's possible to get rid of the fractions here, but you have to multiply by something. You can't just multiply by 5, because that's not going to get rid of the 4's. And we can't just multiply by 4, because that's not going to get rid of the 5. So if we multiply by the lowest common denominator, though, that will get rid of all the fractions. So the lowest common denominator of 4 and 5 is going to be 20. And so I want to multiply both sides, everything, by 20. So I'm going to write that in here. This is going to be times 20. And put this whole thing in parentheses. I want to multiply everything times 20. So if I multiply the right side by 20, you have to multiply everything on the left side as well by 20. And so let's make a little note of this right here. This is what we're doing. We're multiplying. So multiply by the LCD, lowest common denominator, of 4 and 5 in this case. but whatever you have of the fractions to clear the fractions. We're trying to clear the fractions. And then after that, we're trying to isolate the variable, get the variable by itself, solve for the variable. So multiply by the LCD of 4 and 5, in this case is 20, to clear the fractions. So then at that point, we would be taking 20 over here, distributing it through, because we've got two terms added together, we've got something multiplied by that on the outside. So when that happens, when we do that, we would have 20 times 3x plus, or 3x over 4, excuse me, plus 20 times 1/4 would equal 7/5 times 20 over here. And it's okay that I write it to the right side instead of the left. That doesn't make a difference. I could write it on the left side, but again, that doesn't really matter. I think a lot of you have better luck with fractions when you make them both fractions, so we could write this over 1. Let's do that for now. I think that's helpful for a lot of people. And then you can cross cancel. We can cross cancel here. The 20 and the 4 will become a 5 and a 1, because 4 goes into both of those that many times. Same thing here, 5 and a 1. My 5s, man, not doing so good with those right now. And the 20 and the 5 here can cross cancel. That'd be a 1 and a 4 there instead. And so then with multiplication of fractions, you just go straight across. We've reduced as much as possible already, so there shouldn't be any more reduction necessary. 5 times 3x would be 15x. You'd have that over 1, but that would still be 15x. So I can leave that like that. 5 times 1 here over 1 times 1 would be 5 over 1. So I have 15x plus 5 is going to equal, and then on the top here, 7 times 4 is 28, and then 1 over 1, or 1 times 1 is just 1. That'll be over 1, which is just 28 then. So at this point, our different color, let's use this to finish it up. So pretty straightforward algebra problem from here. Hopefully we're used to those things by now. But this would be subtracted there, minus 5, trying to get that variable by itself, to isolate the x, get that all by itself. So 15x equals here 23. And you divide by 15 to finish this up. 15 would cancel here and here. You'd have x equals 23 15ths, sorry. Or you could write that as 15 goes into 23 one whole time, with you'd have a remainder of 8. So with 8 left over, you could write that either way. You could even write it as a decimal if you wanted to, if that was an acceptable format for your answer. But I'll just leave it as those two. For right now with the video, I want to keep this video as short as I can while hitting everything that I want to hit. So if you want to, I would say, good idea. Definitely you should be doing something like this on a test or on your homework or classwork. Plug it back in and see that it works. But I'll leave that to you. So you could use a calculator to plug this back in for x and to check and see that that actually worked out. Example 3. Example 3, I want to show you. Oh, I'm not going to tell you yet. I'm going to keep it a secret for now. So 30x minus 2 equals 7.5 times 4x plus 10. So yeah, I threw a decimal in there. Let's see if we can handle that. But that's really not the big thing here. And so at this point, nothing to do over here yet. I do need to distribute this though. So let's circle that in our different color and show that distribution. That's going to be the same thing over here, 30x minus 2. But on the right side, we'll have, this will be 30x. 7.5 times 4 is 30. So I have 30x, and then move the decimal one place. When we multiply by 10, you'd have 30x equals 75. So this might start to look a little weird to you, and if it does look weird to you, that's actually a good thing. You're recognizing something relatively out of the ordinary with solving linear equations like this in one variable. So I'm going to subtract 30x from both sides. I noticed that that would get rid of the x's on one side, and it also actually happens to get rid of the x's on the other side too. Doesn't happen very often like that, but occasionally you might see something like that. And so I notice that's going to give me 0. So I'm just going to bring down what I have right now and see what I can say about that. So think about this. Just think about this logically. Negative 2 equals 75. When is that true? How about never? That's never true, right? So this can't happen. Negative 2 never equals 75. And so if something's never true, this isn't our final answer, but this is explaining why the answer is what it is. This is never true. You get something equals something that can't happen, that means how many solutions do you have? You have no solutions. So this is never true, so no solutions. So this could happen. This is something that a lot of students might see a problem like this. And if they don't know to possibly expect this, they would see that and they'd be like, huh, I must have done something wrong. Mr. Wagner, can you help me out? No, you got it right. You're good. It just means it has no solution. And so if you were to graph these actually as lines, which we'll be doing later in this chapter, in chapter 6, you would find that these are parallel lines. They never cross, they never touch, meaning they have no solution. They have no intersection, means they have no solution. Let's check out a fourth example in a similar sort of idea here, or with a similar sort of idea. We'll see what I'm talking about in just a second. So let's say I have 10x plus 6 equals 4, and then times the quantity 2x plus 4. And I also have plus 2x minus 10. So to start, distributive property, let's apply that through, and let's see what we get. So 10x plus 6, that's still what I got here. I can't combine any like terms on the left side. Here I've got 8x, and I've got a plus 16. There was a positive 4, so I multiplied everything by a positive 4. This would be 2x and minus 10. So now let's combine like terms on this side. I've got 10x plus 6 is going to equal, well, that would be 10x. And then 16 minus 10 would be, plus 6. Interesting. So if I could do this, I could subtract 10x from both sides if I wanted to try to quote-unquote get the variable by itself, but doing so actually gets rid of the variable on both sides again, just like we saw in example 3. On this one, though, you get 6 equals 6. So here we had negative 2 equals 75. That's never true. But when is 6 equal to 6? Well, that's always true. There's never a time when 6 doesn't equal 6, when a number doesn't equal itself. And so what can we say about a problem like this? We can say that this is always true. So, how many solutions do you have? You actually have infinitely many solutions. And again, when we get to the graphing part of this chapter, we may be discussing this a little more in depth. But if you were to graph this expression and this expression, use slope-intercept form, that type of thing, they'd actually be right on top of each other. They'd be the same exact line in terms of if you said y equals this and y equals that. But infinitely many solutions. In this case, you can plug in any number for x on this side and this side, and it's always going to work out. And so another way for this equation to say what that is, or to say or talk about what it is, you're going to have any value, or in other words, all real numbers for x work. So any value for x will actually work out. And then example 5, let's check this out. Suppose the cost of water in your city, so that water that comes out of the tap, it's not free, but it's pretty close to being free in terms of just like the cost of 1 gallon. You'd be surprised how much money you could save as long as you can trust your city's water supply instead of buying bottled water. But we're going to say it's $2.65. You might say, well, that's a lot of money for water. But let's say it's for, and I'm not sure the current data right now, but we're going to pretend it's for 650 gallons used. Our book has an example similar to this, example 14, where they have a lower price for a higher number of gallons used. So I'm accounting for inflation a little bit. Our book's a little older than this video for sure, and so accounting for inflation, maybe it's something like that. But we're going to ask, what is the water bill if 10,000 gallons are used? And so this one I'm bringing up as a problem here as we review our algebra skills, because a lot of students will look at that and say, oh, it's a word problem, I can't do this, or say, I don't know how to start this, it doesn't make any sense to me. Well, what are you trying to do here? We're trying to figure out the cost of the water bill, the total, if you have 10,000 gallons. So if I compared 650 gallons to 10,000 gallons, that comparison should be the same as $2.65 to whatever my cost is for the 10,000 gallons. In other words, I can set up something called a proportion. So a proportion is just something that equates two ratios or two fractions. So we can set up a fraction here, and it's going to equal another fraction here. And for right now, I'm going to use units as I plug stuff in. I'll drop the units as I work the numbers out. But $2.65 is to 650 gallons as, we don't know how much money, let's call it X dollars. So let me use a dollar symbol in front of there instead. As X dollars is to 10,000 gallons. And so this proportion is going to help us solve our equation, or solve for what X is. This is our equation, the proportion is the equation here. But let's make a quick note that this, in a proportion, you must make the same comparison. Notice I compared dollars to dollars, and here gallons to gallons. You must make the same comparison in each fraction of the proportion. If this is going to be valid, that has to be the case. And now let's solve this for X. So how can we do that? Looks like we can cross multiply. So hopefully you remember something called cross multiplication. Let's use our different color to show that. It's not that I'm crossing out the equal sign, it's just that I'm trying to represent cross multiplication. So the equal sign's still there, but I want to multiply this by this and this by this. And so that's going to give me 650x, and notice I'm going to drop my units right now just to make the numbers easier to think about, and then I'll put the units back. I know it's going to be in dollars because that's what I'm solving for. I'm solving for X dollars. And then 265, so 2.65 in other words, times 10,000, or in other numbers. And so let's multiply this together. You'd have 650x equals, multiplying by 10,000, you got 4 zeros, so you're going to move the decimal place 4 spots. You'd have 26,500. And then finally, let's get out a different color and divide by 650. Divide by 650 here. That'll cancel there and there. You're left with x equals, and if you put that into a calculator, you get approximately, I'll bring up the calculator just a second here, just to double check the work I had done before. So 26,500 divided by 650. And did I do that right there? Let me double check that one more time. I didn't double check my numbers before I typed that in. I did do that right. I did something wrong earlier. Good thing I checked. Way to double check your answers, Mr. Wagner. Thanks. So $40, and let's round this off. It's going to be money. They're going to not charge you for a portion of a penny, so they'll round this up to 77 cents, it looks like. So $40.77 approximately is going to be your answer. I see what I did wrong before. I actually messed something up earlier in the problem. So good thing I checked there. So we get $40.77. You might say, wow, that's a lot for water. I'm just going to go buy a bottle of water. But remember, this is 10,000 gallons, and for $40.77, you're buying 650 gallons for $2.65. That's basically meaning you're taking $2.65. If you divide that by 650 gallons, you are paying this much per gallon of water. It's 4/10 of a cent for per gallon of water. Now you can go buy your water bottles for $1 for, what are these water bottles? Like, well, you're lucky if you get 16 ounces. 32 ounces, pretty good deal for a water bottle, I guess. But if you get it out of the tap, if that's good water coming out of your tap, and you can get it for less than a penny a gallon, I'd say go with that. It kind of just depends on how good the water is in the city you live in. And that's going to do it for me here. Hopefully that helps you and will cause you to think twice. If you're making certain mistakes, you're not going to make those same mistakes before. In this type of situation, distribute the negative sign. This type of situation, multiply that by the LCD. As we're going here, you might see something like this again. You might see no solutions or infinitely many solutions. And again, with proportions, just make sure you're comparing quote-unquote apples to apples and oranges to oranges, dollars to dollars here, gallons to gallons. Whatever your units are, compare the same things as you go across, and you'll be good to go. Okay. Okay, have a good rest of your day, and I'll see you guys later.